Theoretical recap. HTTP, HyperText Transfer Protocol, operates at Layer 7, application, of the OC model, sitting on top of TCP, Layer 4, IP, Layer 3, and ultimately Ethernet, Layer 2. When a browser sends an HTTP request, it first establishes a TCP connection via the three-way handshake, SYN, ACK, ACK, then transmits a plaintext request containing a method, GET, POST, PUT, DELETE, a target path, headers, host, user agent, content type, cookies, and optionally a body. The server responds with a status code, 200 OK, 301 redirect, 404 not found, 500 server error, response headers, and a body. Because HTTP is unencrypted, every field is fully visible in a packet capture, which is precisely what makes Wireshark so powerful for analysis and so relevant to security work. A common beginner mistake is confusing the TCP stream with the HTTP exchange. Wireshark shows you individual packets at the network level, but you can reassemble the full HTTP conversation using follow TCP stream. Another frequent error is ignoring the TCP handshake packets before the first HTTP line. They matter for understanding latency and connection state. Mental model. Think of HTTP as a letter, application layer, inside an envelope, TCP segment, inside a parcel, IP packet, delivered by a courier, Ethernet frame. Wireshark lets you open every layer of that parcel. Finally, remember that DNS resolution happens before the TCP connection. You should be able to spot the DNS query and response in your capture before the HTTP traffic begins, linking directly to your previous DNS lessons. Workshop brief. This workshop puts into practice everything covered in the recent lessons on OC layers 4 to 7, HTTP, DNS, NAT, and TCP/UDP. Your goal is to capture a real HTTP exchange using Wireshark, dissect it layer by layer, and extract meaningful security-relevant information from the traffic. You will work on a controlled, authorized target, your own machine and a local or publicly accessible HTTP server, and produce a written analysis report. The workshop is designed to take approximately 3 hours of focused work, spread over up to 3 days if needed. You must submit your solution before the deadline expires. Step 1. Environment Setup. Install Wireshark on your machine if it is not already present, available for Linux, Mac OS, Windows. Identify a suitable HTTP target. You can spin up a simple local HTTP server. Python's built-in HTTP.server module works perfectly. Use a deliberately vulnerable application such as DVWA, or any plain HTTP site you are authorized to test, or simply browse to a website that still serves content over plain HTTP, not HTTPS. Make sure you know which network interface carries the traffic you want to capture. Use IPA or ipconfig to identify it. Verify that your capture environment works by starting a capture session and confirming that packets appear. Do not start your actual capture yet. Step 2. Capture the HTTP exchange. Start a Wireshark capture on the correct interface. Apply a capture filter if you wish, for example, TCP port 80, to limit noise. From another terminal or your browser, trigger an HTTP GET request to your target, ideally a request that also loads secondary resources, images, CSS, JS, so that you have multiple HTTP transactions to analyze. Also trigger at least one HTTP POST request if your target supports it. A login form or a search field is ideal. Stop the capture after the exchanges are complete and save the capture file, .ppap or .pkpn. You will need this file for your analysis and must include it in your submission. Step 3. Dissect the traffic layer by layer. Using Wireshark's display filters and packet detail pane, work through the following analysis tasks without skipping any layer. First, locate the DNS query and response that preceded the HTTP connection. Note the query domain, the returned IP address, and the transport protocol used, UDP or TCP. Second, identify the full TCP three-way handshake. Note the source and destination ports, the sequence numbers, and the timing between SYN and acknowledgement. Third, isolate the HTTP GET request. Expand the HTTP layer in the packet detail pane, and list every request header present, host, user agent, accept, cookie if any, etc. Fourth, locate the HTTP response. Record the status code, the content type, the content length or transfer encoding, and any security-related response headers, or the absence thereof. This is security relevant. Fifth, use follow TCP stream to reconstruct the full human-readable HTTP conversation. Pay attention to whether any sensitive data, credentials, session tokens, personal information, appears in plain text. Step 4. Security Analysis. This step is the core of the workshop and the one that requires the most analytical effort. Based on your capture, answer the following questions in your report. What information could an attacker on the same network segment extract from this HTTP traffic passively? Are there any cookies visible? If so, are they flagged as HTTP only or secure in the response headers, and what does their absence mean? Does the server expose its software version or framework in response headers? Server, X powered by? What does this reveal, and why is it a risk? Could you identify the user's browser, operating system, and accepted language from the request headers alone? Think about what a reconnaissance phase, as covered in your professional objectives around PenTest methodology, could harvest from a single unencrypted HTTP session. Document each finding clearly, citing the specific packet number or the relevant line in the TCP stream. Step 5. Report and Submission. Write a structured analysis report in PDF or Markdown format. The report must include a brief description of your test environment and target, the annotated PKP file or selected screenshots of key packets with packet numbers clearly visible, a layer-by-layer breakdown following the tasks in Step 3, your security findings from Step 4 with evidence, and a short conclusion explaining what this exercise demonstrates about the risks of unencrypted HTTP in a real-world context and how it motivates the use of HTTPS, HSTS, and secure cookie attributes. The report does not need to be long. Clarity and precision are valued over volume. Include your PKP file alongside your report in the submission archive. You are free to consult all previous course materials, your own notes, and any internet resource you find useful. You may work alone or ask peers for guidance, but the analysis and the writing must be your own. The recommended time for this workshop is 3 hours. Manage your time accordingly and submit before the deadline.